Oh, that was painful, wasn't it? Don't worry, be happy. I have no idea what face Jason or Joey are making. Don't bother to show me, but I am excited. Ernesto's not wearing a blue shirt, so we're good. Something new today. That's good to know. All right, ready to get started? Today we're going to talk about center of mass. And although everything I'm about to teach you is part of our curriculum, it is terribly unlikely you'll have to do this on the exam. So I'm not telling you not to know how to do this. I'm saying that this is just like step one. Like you need to know a little bit about this, but what you're going to do on your exam is bigger than this, much bigger than this. So the only time you might have to use what we're about to talk about on the exam is probably if you're asked to figure out the center of mass between like two planets. That has shown up on the exam before. And that's the only time you've used this particular thing. What we're going to have to do is a little different. So towards the end of our discussion, I'll be telling you how what we're going to need to do on the exam is different than what I'm going to show you today. But today is just a start. If you'll do me this honor, though, could you look up on your equation sheet the center of mass equation? Mostly because I want you to be a little scared. You might pee a little, and that's okay. You know, I'm sure. Well, actually, it's not okay. But in case it happens, don't tell anybody. Find it yet? It's there. Who's got it? Bunch of sigmas? You see all those sigmas? Those summations? Yeah, there it is. There it is. That's right. X center of mass is the sum of m times x over the sum of m. It looks something like that. That does not tell you very much. So although you might write it down, you already have it on your equation sheet. Truthfully, this isn't the center of mass. What you have on your equation sheet isn't the whole thing. It's just a part of the story. Not even, that's like telling you that Newton's law is F equals ma. Does that really tell you what Newton's law is? Not even remotely. The center of mass is the balance point. You can think of it that way. If I push something towards the edge of the desk, if I can get it just to balance and teeter on the edge of the desk, I have found its center of mass. But that's really not all the story, because the center of mass is a location. That's the biggest misnomer about the center of mass. People have this idea that the center of mass is a mass, but that's not it at all. The center of mass is a place. It's a location. It's where the average mass of the object is. So this formula is the same formula you learned in the 6th grade for calculating a weighted average. It's the same thing. In a weighted average, if you'll recall, instead of just taking the numbers and then dividing by the number of numbers, a weighted average gave more prominence to some numbers over others. Often population calculations are weighted averages, where you weight perhaps a number based on how many people have that same number. So that's a weighted average. This is similar. In this case, X represents the location of a piece of the object, but that piece might have different masses depending on what that piece is made out of. You made it very clear to me that mashed potatoes needs to be on my list next year. If I produce a sphere of mashed potatoes, it is very likely that the center of mass of that sphere is at the very center of the sphere. Why? Mashed potatoes are relatively uniform, unless you're doing it wrong. I mean, does anybody like lumpy mashed potatoes? Now, some of your parents probably put stuff in their mashed potatoes. I'm not a fan. I want my mashed potatoes to be nice, smooth, and consistent. On the other hand, who needs mashed potatoes when you have stuffing? But if I produce a sphere of stuffing, there is no guarantee that the center of mass is at the center of that sphere, because it's got onions and celery and bits of turkey butt in there and breading, I think. I don't know. Who knows what's in there? Some people put like sausage and other stuff in there. I have no idea, because every piece of mass in it is a different value. And because of the inconsistency and non-symmetry of it, I can't count on where that center of mass is. I have to take each location and the mass of each piece at that location and do a weighted average to figure out where the center of mass is. But should I do all of that, I will find the point where it would balance, where I could hold it in three-dimensional space and it would be perfectly balanced on all sides. Sometimes the center of mass is called the center of gravity, but they are not the same thing. There's some technical differences between them, but there's also some big differences. The center of mass exists even if you're not in a gravitational field. But the center of gravity is where we say your mass is concentrated for the purposes of how gravity acts on you. So there is a difference there. It seems subtle, and there are more nuanced portions of why center of gravity is a different topic than center of mass, but it's not important enough for us to discuss, except that they could use these words interchangeably on the AP exam. I will only use this, I think. I don't think I'll ever use center of gravity. But when we talk about torque and teeter-totters and stuff, it should be more appropriate for me to use center of gravity. And center of gravity has appeared on the AP exam. Just note that center of gravity is merely how this gravitational force acts at the center of mass. Does that make sense? A little bit, maybe not. We'll see. But I want to focus on calculating the center of mass. I do want you to understand, though, that this formula is one-dimensional, but it is a vector formula. It takes its direction from the value of x in the formula. But if you actually wanted to find an object's center of mass, and it was more than one-dimensional, you would have to do this again for the y direction, and again for the z direction. The center of mass would have to be added in all three dimensions in order to find the actual center of mass, which is why, truthfully, it should be written r center of mass, where the summation is based on a three-dimensional vector for the location of the center of mass. The fact that the equation sheet doesn't do that kind of hints you at the idea that they're just kind of focused on a one-dimensional problem. That doesn't mean that they're going to give you a one-dimensional problem. They have given two- and three-dimensional center of mass problems in the past, usually exploiting some amount of symmetry in the problem. Now, I do want to make sure you understand that in real physics, there's more to it than this. And there is an expectation by me that we will learn about doing the center of mass as it should be done when you guys have successfully made it to a point in calculus where we could find the center of mass for a smooth object. This has been on the exam, even though this equation isn't on the equation sheet. And it's been recent. In the last 5 years, there's been a contemporary exam that's had you calculate the center of mass of a non-uniform object, which means having to integrate the mass. It's not particularly terrible, but it was a shock to all of us when it was on the exam. So these are different ways that we calculate the center of mass. We are going to focus right now on how to calculate the center of mass for a one-dimensional arrangement. So let me put down a number line. There's my number line. And I'm going to come up with, say, I don't know, let's go with 3 or 4 objects. No, not that object. There's object number 1, object number 2, and object number 3. And let's say, make that one bigger. Yeah, there we go. Biggest in all the land. Let's go with 15 kilograms, 5 kilograms, and 10 kilograms. And let's say that these are 5 meters apart, and these are 3 meters apart. So I have 2 goals here. The first is to show you technically how to calculate center of mass, how this all works. The second is to kind of prove a point about what the center of mass actually is. I'll remind you, the center of mass is a location. It's a place. So based on what I've written here, where do you think it is? A, B, C, or D? Raise your hand if you think it's at A. B, C, or D? Right, the vast majority of you think it's a B. That's probably a good thing. If I look at this, it looks like it's heavier towards the left and to the right. It's certainly not going to be at A or D. That's a little bit ridiculous. Now, to calculate center of mass, the first thing you must do, and this is the most important and the one that people forget, is you must come up with a frame of reference. Remember, the center of mass is a location. So if I want to tell you where something is, generally I have to tell you where it is relevant or related to what starting point. Like I pointed to B, but B is all here. Where is it really? Is it closer to the 15 than to the 5? I need a way of measuring it. I want to know how many meters away from some fixed reference point it is. So the first thing you really need to do when you're tasked with one of these problems is come up with a reference point. Now, I'm going to choose a reference point for us, but I want you to note that most of the time, the reference point has been chosen for you. Like if this is going to pivot, it'd be appropriate for us to know that the pivot point is probably the right place for the reference. If it's a gravity problem, generally you make the pivot, you make the reference point like the one of the objects, one of the planet's centers. But the truth is, I can make my reference point here if I wanted. It'd be stupid, but I could do it. If there's a reason why, I don't know. So I'm going to choose our reference point for us. And I'll tell you that it's almost always easier to make your reference points one of the objects. Almost always easier to make one of your reference points the objects. One of the objects. I'm choosing the middle one on purpose because I want to exaggerate the idea that the center of mass has to be a vector. So when I choose this as my reference point, I'm doing so because I have mass on the left side and on the right side. I need to differentiate left from right, so minus and positive is how I'm going to do that. And it's a vector. And I've just arbitrarily made the left negative and the right positive. So let's begin. Remember, it's a summation of the size of the mass times its distance from our reference point, divided by the summation of the mass. I hope you guys noticed that the denominator of this fraction is just how massive the object is. In our problem, the object is 30 kilograms. That's the mass of the object. So the bottom is just going to be 30 because it's 30 kilograms. That was true with this too. The integral of dm is just the mass of the object. Now, the top, a little more, I've got 15 times its location, plus 5 times its location, plus 10 times its location. Now, I'm doing this on purpose to be as explicit as possible so that everybody can kind of have access to this. The 15 kilogram mass is -5 meters from my reference. So I'm going to put -5 here. The 5 kilogram mass is at the reference, so 0. And now you see why it's nice to put the reference point on one of the objects because you zero it out. And the 10 kilogram mass is 3 meters away, and it's on the right, so it's positive. 15 times 5, 75. 10 times 3, 30. So this is going to be, what, -45 over 30? Am I right? Oh, good. I like it when I'm right. I believe that's -3/2. Right? Cancel out 15 on both sides. -3/2, which means the center of mass is 1.5 meters from the 5 kilogram mass to the left. Right? 3/2. This is where the center of mass of the system is. It's a location. It's where I thought it would be too, somewhere in B. But now I know exactly where it is. If I put this as a pivot point, it will balance perfectly with an equal amount of mass distributed uniformly on both sides. Do you guys remember, you guys were in my class last year doing the teeter-totter lab where you hung the weights on both sides of the meter stick? We never talked about it last year. We did it as a torque experiment, but we were actually finding the center of mass of the system because it was the same idea. fact, that's how you would do it. Now, I want to prove a point. So to prove that point, I want to remember that it doesn't matter where our reference is. The center of mass is a location. That location doesn't change depending on the reference. That's where my center of mass is. So let's set the reference point over here, 2 meters away from the 15 kilogram mass. We should get the same location, right? So that's 3.5 from the 15. So I expect to see this at 5.5 meters. That should be our answer. See that it is. Take a minute and redo this with our new reference and show that it should work out to be at the same place, even though this number is going to be different. We got to hurry because we only have 5 minutes left. Oops, not 7, 2, 7, 10. 30 plus 35 plus 100. That's just silly. (165/30). Does it get smaller if we start dividing out by 15? Bet it does. What does it work out to? What is it? 5.5. That's right. It's exactly where we said it was going to be. 5.5 meters away. So remember, your reference determines how the answer is portrayed, but the location is a place that's the same all the time. This is not what you're going to have to do on the exam. This is very unlikely on the exam. What's more likely on the exam is for them to ask us, perhaps, what is the velocity of the center of mass? So what we're likely to have on the actual exam is, say, 3 objects that are moving, maybe in a uniform way, maybe not. And they may want the velocity of the center of mass, which means taking the derivative with respect to time of the center of mass, which would mean changing these not to positions, but to velocities, and then calculating the velocity of the average center of mass of the system. That's a very likely question on the exam. So finding a center of mass, that's not what we're going to do. We're going to be doing something more than this. Although I'm going to give you some practice like this, it's likely that what we'll expect to see is something like this on the exam. Generally, when they've asked this on the exam, it's been one-dimensional. So they've asked about the motion of the center of mass in a one-dimensional way. Do you remember us talking about how on a Atwood machine, a mass is going down while another mass is going up? Well, you can imagine calculating the center of mass of that system as it descends. What's the speed of the center of mass? That's the kind of question they've asked on the exam before. But they've also asked questions like this. And so I want you to be prepared for qualitative questions too. Imagine a square piece of metal, something like maybe a long piece that's been bent into a square. And they take this square and make, how should I do this? I gotta do this right. Give me a second. Gotta work this out in my head. They take this square and they take away a portion of it. And then ask you, what would that do to the center of mass of this object? So it was like this before. You could probably assume that if it was like that, the center of mass was, say, here. But then if you were to break off a piece of it, how would that shift the center of mass? Clearly there's less mass at the top, so it's going to go down. But because of the distribution, it'd probably go to the left too, right? So this kind of question has appeared on the exam, where they've tried to get you to have an idea about how a two-dimensional system would be affected by its change in its shape. So this is the style of question that we should expect. This was multiple choice. This was on an AP exam a couple years ago. So we're going to end here because I think that's enough for us for one day, not to mention the fact that the bell rings in like a minute. So are there any questions about this? Seems pretty straightforward. We're only going to spend one more day on center of mass, but I am going to be posting some homework for you that has a couple of questions. But the bulk of what we're going to talk about is going to be systems of particles, and we're going to start that end of the class tomorrow or beginning of the class on Friday. So you guys at home, any questions for me? Well, it's been real and it's been fun, but you guys are welcome to take off whenever you're ready. It's nice to see you all today. Goodbye. Enjoy your afternoon. It's cold out there today. That's why I was trying to get the thing to play the Baby It's Cold Outside song, but I got nothing.
Yeah, Mr. Shelton.
Bye-bye. Have a good day.
John says bye as well.
Oh, tell him I said hello and then goodbye. See you guys.
Adios.